Alright, so previously on section 1 we learned about dimensions and we learned about how to change things into a matrix form that might have been in a table form. We also talked about elements, different elements of the matrix and that notation. So here in 4.2 we're going to talk about the operations with matrices, but just a few of them. We're not quite going to get into big time multiplication. We're going to talk about adding, subtracting, and a different type of multiplication. First, adding and subtracting. This can only happen when your dimensions match. So please follow the yardstick. Dimensions must match. So a 2 by 2 can only be added with a 2 by 2 or subtracted. A 3 by 16 can only be added or subtracted with another 3 by 16. Here's why. If I have matrix A and matrix B, you notice that they both match 2 by 2s. If I wanted to add the 1 with its corresponding spot, the 10, I can do that. That would be 11 for the new A plus B matrix. But let's say that I had a 2 here, and let's say that I did not have the 11 and 13 column. Matrix B was just that. I would not have a matching component for the 2. So that wouldn't work. So that's why we have to have the same dimensions. But we do in this case. So the 2 would combine with the 11 to make 13. The 3 would combine with the 12 to make 15. And the 4 would combine with the 13 to make 17. And I'm just showing you an addition problem. Subtraction works the same way. 1 minus 10, 2 minus 11, 3 minus 12, and so on. So, if we talk about what we really just did in element format, we took an element from A, 11. So row 1, column 1. That was the 1. And the B, row 1, column 1. That's the 10. So 1 plus 10 is 11. And we did that for every element. Row 1, column 2, which was the 2. And row 1, column 2, which is the 11. That gave us the 13, as you see there. Now, you can follow those 4 examples and see if you can make sense out of it. But lastly, I wanted to show you a situation that would not work. Element 21, so row 2, column 1, column 1 is a 3, and element 22, the 13. I would not be able to add the 3 and the 13 because they are not corresponding locations. They're not corresponding elements. Corresponding means they are in the same place in different matrices. So that would not be possible. That's just an example. So you can only add and subtract the same locations. Now that was adding and subtracting. You have to have the same elements, or the same dimensions. With scalar multiplication, you're going to be multiplying one matrix by just a number. So let me show you what I mean. If we have matrix Q, and it's going to be a 3 by 2 matrix, 3 rows and 2 columns, I want to know what 3Q is. What that means is, what is 3 times Q? So, all we do is we write it down. What's 3 times Q? Well, that's Q. And we just multiply the 3 times every single element in that matrix. So, the 3 is known as our scalar. There's a lot of physics involved with the word scalar, but right now, for our Algebra 2 sake, we're just going to know that scalars are simply like constants that we can multiply by. And so as you see, 3 and 2 is 6, 3 times 1 is 3, 3 and negative 1 is negative 3, 3 and 3 is 9, and so on. We get 0 and 15 from 3 and 5. Hopefully that makes sense. But what I want you to notice is that the result of 3Q is not any different dimensions-wise from the original Q. It did not change dimensions. It's the same thing, 3 by 2 matrix. So what we have here is the original matrix Q is 3 by 2, and the new matrix 3Q is also 3 by 2. It's just a blown up version because we multiplied it by 3. Now scalars can come in all shapes and sizes. This could be a decimal, it could be a fraction, it could be a 3, it could be 100, it could be anything, as long as we're multiplying it. Lastly, this is not really associated with scalar multiplication, but I do want to show you how we can incorporate some of our old properties, commutativity and associativity. So the commutative property, if you remember, was simply switching the places of two values. But in this, I want you to think of the A and the B as matrices. So if we can add matrix A plus B, that should equal then B plus A. Go back to your first example on this slide. If we want to also think about associativity, if we can add A and B and then add that to C, then we should be able to do B plus C and add that to A. Now I hope you're noticing that the only way this is going to work is if we have the dimensions that allow it to be so. So with addition and subtraction, you can only do this with the same dimensions. They have to be the same. So 2 by 3s and 2 by 3s. But I also want you to notice that A plus B is the same as B plus A. We cannot do that for subtraction. We might get different answers. In fact, I'm pretty sure in most cases we would get different answers. So these two properties, I say that they're legal because they will always work if the dimensions are the same. Alright? And we'll talk about some other exceptions later on in class and why things won't work for subtraction. Alright? So come into class with any questions you have, and always remember, flip, don't flop.